Good evening, doctor and classmates. My name is Rahma Aal Khulaifeen. Welcome to my presentation, which is about biochar effect in soil quality. In this presentation, I'm going to discuss the following. What is biochar? Physical and basic properties of biochar, biochar adsorption and desorption mechanism, biochar impact in soil quality, and finally, the further challenges and further researchers needed to be done in biochar. Before discussing what is biochar and its effect in the soil quality, we should think a little about what do we mean by soil quality. Soil quality can simply be defined as how well a certain soil performs with a defined environment. Basic soil functions are all influenced by soil qualities, like storing and recycling nutrients, filtering, buffering, immobilizing, and detoxifying organic and inorganic materials. There are many factors that are responsible for soil quality declines, such as soil degradation, which is a result in a decline in organic matter content in the soil and a decrease in biomass, carbon, and nutrients. Another factor that contributes to decreasing soil quality is soil pollution. Continuous cropping and excessive use of chemical fertilizer can quickly reduce the organic matter content in the soil, which affects beneficial organisms by using soil structure decline and soil acidity, reducing plant growth, altering the pH of the soil, increasing insect populations, and even leading to soil pollution. What is biochar? Charcoal is the most well-known application of biochar. Biochar can also be defined as the solid byproduct of biomass pyrolysis, which has been produced and used for many centuries. The uses of biochar are quite varied, ranging from the generation of heat and power to cleansing of fuel gas, to usage as a building material, to medical applications. It has become more and more popular in recent years as a substitute for fossil carbon carriers in a number of these applications in an effort to cut down on greenhouse gas emissions. Now let's go to the physical properties of biochar. The first one is surface area and porosity. There are many characteristics of biochar that are connected to its surface area and porosity. For example, the surface area affects the accessibility of surface charges, which affects the cation exchange capacity. The ability of the biochar in storing water depends upon the interconnectivity of the pores and their porosity. There is a strong connection between biochar reactivity and active sites. In contrast, a large accessible surface area is a necessity for a large number of active sites. Surface area and porosity play an important role in biochar applications. For example, biochar generally acts as adsorbent, and its capacity for absorption is mainly connected to both surface area and porosity. The biochar's porous structure helps in sorption process pore filling phenomenon. Biochar has gained popularity in recent years in environmental applications such as wastewater treatment, soil remediation, and gas pollution capture due to its high absorption ability. For both organic and inorganic contaminants, including volatile organic chemicals, insecticides, dyes, it has been demonstrated to have a high sorption efficiency. Additionally, Biochar is often used as a soil amendment due to its porous composition and large surface area. The second property of biochar is adsorption and desorption mechanisms. The absorption mechanisms in biochar take place in the carbonized and non-carbonized fractions that are located on the heterogeneous surface of biochar. Sorption occurs when a solid sorbent's interfacial layer becomes denser or as a result of molecular exchange with the sorbate. There are three main sorption modes depending on the intermolecular interactions that characterize the sorbate-immobile phase interactions. These include ion exchange, chemosorption, and physisorption. The physisorption route, which is more commonly used in environmental systems, can be classified into adsorption and absorption depending on how the sorbate interacts with the solid. Adsorption is the attachment of a molecule at the interface between a liquid and a solid surface where the sorbate molecule cannot pass through the solid's atomic or molecular lattice. The degree of organic pollutant solubility influences the rate of adsorption on biochar due to interactions over the hydrophobic sites. So, if the pollutant has a hydrophobic functional group, it can be linked to hydrophobic biochar. The total volume of the microbes and mesopores affects the absorption of organic contaminants onto biochar by profiling. Water-soluble pollutants can also precipitate on the surface of alkaline biochar. Due to the precipitation of insoluble phosphate, biochar decreased the mobility of the heavy metal phosphorus in an aqueous solution. Because the pollutant penetrates the biochar surface deeply, the adsorption capacity of biochar typically rises as the ionic radius of the pollutants falls. As a result, when thinking about adsorption on a biochar surface, the atomic or ionic size of pollutant should be taken in consideration. Another adsorption mechanism is the electrostatic interaction between the biochar surface and organic pollutants. The metal exchange with alkaline metals, potassium ion and sodium ion present in biochar surface is responsible for this interaction. Now let's move to biochar impact in soil quality. We'll start with pH. pH is an important factor affecting soil fertility. A change in soil pH can influence the soil's environment and increase the nutrients that are available to plants. Additionally, the altered soil environment promotes microbial growth and accelerates chemical process in the rhizosphere. Many studies found that adding biochar changed the pH value of the soil. The best effect was more obvious in the acidic soil due to the alkaline nature of biochar. pH of the biochar, whether it's acidic or alkaline, depends on the feedstock materials used. Some studies found that the biochar pH values were from 5.9 to 12.3 with a mean of 8.9. However, other studies found them to be from 6.2 to 9.6 with a mean value of 8.1. It has been shown in other studies that the alkaline beechwood biochar has highly increased the pH of the soil. Additionally, other studies assure that applying biochar raises the pH of the soil, which in turn encourages the activity of the alkaline phosphate in the soil. Alkaline phosphate activity is increased by 2 to 3 times after the application of corn cob charcoal. These results supports the hypothesis that the application of biochar affects the microbial activity of soil in response to pH variations. The second impact of biochar that it's responsible for enhancing soil water properties through improving soil structure. Application of biochar to the soil affects soil structure, which as a result leads to a change in some soil hydraulic parameters. Through studies, it has been shown that biochar decreases the saturated hydraulic conductivity of the soil and cause a decline in its field capacity, permanent wilting point, and a valuable water content. Additionally, soil water storage and mobility has been directly affected as a result of the increasing connectivity of pore space, number of pores, and soil porosity. This also leads to an increase in soil moisture retention. Increased soil aggregation may also be responsible for an improvement in soil water characteristic following the addition of biochar. There has been a number of studies where a reduction in bulk density has been observed, which can also be an indication of increased soil aggregation. The process of arranging and combining soil particles to create secondary units which have an impact on how water moves is known as soil aggregation. The hydrochloric conductivity and water retention of soils are both improved by the addition of biochar to the soil by increasing the production of macro aggregates and aggregate stability. The third impact of biochar is in soil microbial activity. Studies have shown that the application of biochar to soil increases the number of microorganisms, fungi, bacteria, and actinomycetes in the soil significantly. There are three reasons beyond this. The first one is that nutrients can directly boost soil microbial activity due to the biochar's co-metabolisms and soil stimulation effects. Secondly, the addition of biochar can alert the number of soil physiochemical characteristics, including soil pH, cation exchange capacity, and the availability of water and nutrients. This indirectly affects microbial development and activity. The last reason is interaction between biochar and soil's organic coating and organomineral layer are found, which help to improve nutrients and water retention and ultimately microbial biomass. 4 is the effect of biochar amendment on carbon sequestration in soil. An addition of biochar to the soil improves its fertility, which not only increases the soil health but also captures carbon. The most obvious and appealing method for biosequestering carbon is thought to be the recycling of biomass into biochar. By enhancing the soil's capacity to store carbon, biochar helps in reducing greenhouse gas emissions. The biochar lost very little carbon throughout a lengthy test and modeling process, which reduced atmospheric carbon emissions. The decrease in greenhouse emissions was primarily caused by changes in the emission related to the production of feedstock, avoided emissions related to the use of fossil fuels for bioenergy, the stabilization and storage of carbon in biochar, and the decrease in agricultural nitric oxide emission, which lead to fertilizer cost saving associated with the use of biochar on agricultural land. In general, biochar amendment improve carbon stabilization and decreases carbon dioxide generation. Fifth is impact of biochar in soil phosphorus. Biochar has demonstrated its ability to alter phosphorus availability in soil by preventing phosphorus leaching via sorption and adsorption. According to some studies, adding peanut hull biochar to soil solutions raised the quantity of phosphate there by 39%. The alteration in soil pH and subsequent impacts on phosphorus interaction with other cations, as well as improved retention through anion exchange and phosphorus precipitation, are indicated as potential mechanisms for how biochar affect phosphorus availability. Phosphorus availability in soil is thought to have increased as a result of the biochar reduction of the quantity of phosphorus from 30 to 40% that was sorbed onto ferrihydrite, the most effective iron oxide for adsorption of phosphorus. The surface of biochar absorbs phosphorus, reducing leaching. The large surface area of biochar has a great capacity for absorbing phosphorus in its ionic forms. Thus, biochar affects phosphorus availability and can lessen orthophosphorus leaching from nutrients-rich soil. Finally, effect of biochar on heavy metal concentrations in soil. In comparison to plants cultivated in soil without biochar, biochar consistently decreased the average level of heavy metals in plant tissue. When plants were cultivated in soils treated with biochar, the mean amount of cadmium, copper, and zinc in plant tissue decreases by 38, 39, and 25 respectively. Across all investigations, the reduction in soil heavy metal availability were mainly attributable to the immobilization of these heavy metals onto biochar particles, as well as to indirect effect of biochar on soil characteristic and plant absorption mechanisms. Adsorption, ion exchange, complexation, and precipitation processes are a few of the mechanisms by which heavy metals are immobilized by biochar. In addition to direct interaction with biochar, modifications in soil characteristic brought on by the application of biochar may also indirectly increase the capacity of soil particles to absorb complex and precipitate heavy metals, thereby lowering their availability. Further challenges and future researchers about biochar. Due to its potential to reduce greenhouse gas emission by immobilizing carbon in soil structures, biochar has recently gained popularity as a substance for soil amendment. In order to fulfill sustainability concerns, the current obstacles to using biochar on a large scale are briefly discussed. To date, investigations on the use of biochar as a soil amendment for crop production and soil decontamination have been conducted at both the lab scale and the pilot scale. It is important to note that the majority of research in this area has been done at the lab or pilot scale, and that field investigations are still very uncommon. Therefore, it's advised that future studies translate the knowledge now held from lab and pilot scale application to field application. These studies will be crucial for determining the degree of effectiveness of biochar soil application activity by correlating the circumstances of biochar production, the type of feedstock used, and the properties of biochar and their effects on soil parameters. That was the end of my presentation. Thank you very much for your attention.